write down a trace modal category. You never know when it might be useful. So first, it's a great pleasure. I want to thank the organizers for the chance to speak at Prakash's 60th birthday. I've known Prakash a long time, I guess, since the first licks in 1986. We met. I visited him at Cornell. He introduced me to the whole New Pearl gang at the time. And then it was a great pleasure when Laurie dragged Prakash back to Canada and they set up in McGill. And he's been our beacon to the world of theoretical computer science ever since. And, so I just want to say what a pleasure it's been, as everyone else has mentioned, knowing Prakash all these years, and I hope we will continue some papers we've worked on in the past and haven't brought to back into light. And so this is something slightly different for me, a new direction. This is joint work with colleague at Harriet Watt. I should say here, I wanted to thank officially Gordon and Alex Simpson. I've been on a sabbatical in Edinburgh, in informatics there, and curiously enough, when I got there, Alex turned out to be working on these kind of fuzzy logics, in fact, that I'm going to be talking about. So it was quite a fun thing. This is work with Mark Lawson, who does inverse semigroups. So, how does this work? Jamie, you better help me out.
You better stand there and do slide transitions.
No, stand down. Okay, down, and then that's it. You don't have to point it, you can point it at Prakash if you want. Okay, so,
After the days that we...
so I want to talk about two directions, curious directions that occurred in the literature. And I'll give some history and I'll define all these words, so don't worry. But in 1986, Mundici, a logician in Italy, did some really seriously profound, interesting work on a subject called MV-Algebras. These are Lindenbaum-Tarski algebras of multi-value logic. So it's fuzzy logic, 0-1 value logic. And he showed that these things connected up with George Eliot's program for classification of AF seastar algebras. And since then, in the last 30 years, he's developed a huge school and a considerable amount of work on understanding these MV-Algebras. Coming out of left field, 10 years later, in the mid-1990s, people in Eastern Europe and also Benedict Foulis, I'm not sure if you pronounce it, developed a theory of effect algebras, quantum effects, and quantum measurement, which were curious kind of things on partial algebras. And so what we want to do is to find a setting that encompasses both frameworks based on inverse semigroup theory. And moreover, I want to connect this up with recent work in non-commutative stone duality, so that should give some interest to Prakash. Étale groupoids, pseudogroups, tilings. If I have time today, I'll talk about prefix codes. This is all part of this general framework. The idea is to generalize AF seastar algebras, and the main technique is a graphical technique. It's a graphical language called Bradley diagrams. And a little story there. I was in Marseille visiting a month ago, and I was there, and I was sitting on a bus, and I was reading an article, and a guy sat down beside me, and he looked over my shoulder, and he said, "Oh, you're interested in Bradley diagrams. I have this temporally Lieb algebra, and I'd like to calculate this." And I said, "No." Anyway, the theorem, and I should at least tell you what the theorem is. So, in case I don't get to it. The theorem is the following. We want to try to classify these in the sense that von Neumann gave his coordinatization theorems for projective geometry. I've been reading his papers in the Proceedings of National Academy of Sciences in 1931. They're extraordinary things. Where he talks about the program of redoing geometry by getting rid of points, lines, and planes, and introducing instead the idea of lattice of subspaces in space and abstractly developing a dimension. So we want to do exactly the same thing. Any denumable, countable MV algebra, MV effect algebra whatsoever can be coordinatized That is, there is a Boolean inverse coordinatizing monoid whose lattice of ideals, principal ideals, is isomorphic to the group. However, it's not such a constructive proof, so it's not so easy to see what it would look like in practice. I will mention that. I will mention to you, though, Mundici gave a whole series of examples of interesting enumerable MV-algebras. And in fact, if I can today, I want to talk about the dyadic case, which corresponds to the Carr algebra of the Fermi gas. There are many other ones that we have no ideas about in the case of real. What I wanted to point out is that these algebras here are well-known algebras in the operator algebra community. These last two are two of my favorite ones, and these are the McNaughton free ones. And they'll be slightly related to things that Bessel mentioned in his talk. So what are these things? So they arose in the 1920s. Lukashevitz introduced many value logics. Briefly, they're fuzzy logics. They're not really logics in our sense. They don't have a curry or anything like that. But they're lattice theoretic logics. And they're fuzzy logics with truth values in 0, 1, and also you can take related ones with rational points in 0, 1, or dyadic rational points in 0, 1, or discrete. And he looked at all of those. And I'll just give a brief history. So it was studied by Polish logicians in the 1920s, and in parallel Post. But Post is Polish, so they kept it in the family. Right? Then what it seems to have happened is every 30 years something's happened. So 30 years later, in the 1950s, you had McNaughton, right around 1950, proved a fundamental theorem characterizing the three ones, the three MV-algebras. But this was before MV-algebras were defined, so it was characterizing the Tarski. Then in the 1950s, the model theorist Chang developed MV-algebras. He defined them, he proved the Chang completeness theorem, and he connected them up with lattice-ordered Euclidean groups by quantifier elimination, actually. Then, 30 years later, Mundici and his school started. So we connected up MV-algebras with AF seastar algebras, the work of George Eliot, Evros, and my colleague David Hammerman, dimension groups, Grovedig's K0 functor, and states of probability distribution. Then, recently, 30 years later now, various people are interested again. So Eduardo de Boot, category theorist, has given chief representation theory for MV-algebras. Alex Simpson is working on Lukashevitz's mu calculus, and there's some recent stuff by Carmelo. So what are some MV-algebra after all this? So what it is if you're a linear logician, it's a very strange kind of par monoid. So you take a monoid with par, it's a commutative monoid, negation is an involution, 1, which is negation, and 0 is absorbing, and then finally you have this very strange axiom of Chang, which is symmetric in x and y. Not x plus y plus y is not y plus x plus x. I couldn't figure out what that possibly could mean, so I decided to write it in linear logic. Let x lollipop y be not x plus y. And then you get this interesting Boolean identity. Now this reminded me then to look at Prakash. One time I convinced Prakash, when he's teaching a logic course in computer science, to do my favorite thing, a Fitch-style natural deduction. So there's a little exercise for you, Prakash. He used to call me up late at night and say, let's work through some neat examples. Try to work this out. Well, it turns out not to be intuitionistically valid, but it is classically valid. And you'll have some nice tricks, call CC and so on, to prove it. It's actually quite fun to prove it. So anyway, I'll let you do that. Meanwhile, let tensor be the Morgan dual par, and define less than or equal to the way you do it in algebra. X less than equal to y if the sum z, x plus z is y. And then you get that less than equals to partial order, and tensor is left adjoint to lollipop. There's also strangely a logical subtraction. You can let x minus y be x tensor not y. And then it turns out that minus is left adjoint to par. And there's also some lattice structure.
By the way, Phil,
Yeah.
just to interrupt you, that last formula, if you put y equals false, you get x equals not x, right?
Yeah. Well, we had it, not x is x. So, fundamental example is 0, 1, where not x is 1 minus x. X plus y is x plus y cut off at 1. Later on, when we do effect algebras, those guys, the physicists, don't care about undefined unless they just say undefined. But for us now, we want it to be a total algebra. And then you can similarly just take the induced structure on all the other examples I gave. In fact, Mike Barr already pointed out, this is Don Tellman's post way back. An apparently more general, but not really so much, example is lattice ordered abelian groups. So you take a abelian group, and suppose it's partially ordered, and the partial order is going to be translation invariant. If x is less than or equal to y, then x plus t is less than or equal to y plus t, any t. Take, if it's lattice ordered, it's called an L group, and it then has a positive cone. And in those situations, t plus blank preserves the lattice structure. And now, I think Bart mentioned in one of his talks the idea of having an Archimedean element. So an Archimedean element is when Achilles definitely passes the tortoise. So you have an element U, and you lay out any element of the group, eventually you'll pass it by doing U plus U plus U a certain number of times. So any element G can be eventually dominated by a U for some n. And so in that case, we can now define, in those situations, a G interval, which is all the things between 0 and U. Oops. And you then get these G interval MV-Algebras. They look like this. You have cutoff, subtraction, and addition. You have U minus X for negative, and so on. And these are perfectly fine. Top element is U. All the previous examples are gamma of something. So you can figure out all the previous examples I mentioned. And then Medici showed there's an equivalence of categories between these lattice ordered groups with ordered abelian groups within a unit and these MV-Algebras. So that's fine. And then continuing the historical stuff, I'm not sure how much time.
About 13 minutes.
Okay. Better speed up. Changpu is completeness theorem, and in particular, it has the property that an MV equation holds in 0, 1 if all MV-Algebras. Hence, you have the existence of free MV-Algebras, which are generated from the projections and closed under pointwise operations. And the theorem of MacNaughton was that these are exactly the continuous piecewise linear polynomial functions in variables with integer coefficients. Most of the proofs of this are quite heavy duty, and Medici has 3 or 4 proofs. They all use a lot of topology analysis. But I don't know how many MacNaughton himself originally proved it. But now there's a recent one, Dubuque, purely algebraic proof. You have to develop the whole theory of the Chinese remain theorem, solving congruences in MV-Algebras. MV-Algebras are very much like algebra. I mean, it really is a traditional algebra. And it also, moreover, is very much like analysis. And I'm beginning to slowly take the viewpoint of Bart that I think the more natural thing is effect algebras. So we'll be talking about that in a second.
Yeah. What are piecewise linear polynomials?
So it's just a sum of
a sum of piecewise polynomials?
That's right.
Okay.
And they're just a summation of AIX. So next part of the story is matrix algebras, AF seastar algebras. So a finite dimensional seastar algebra is one that looks like a direct sum of square matrices over C. And this ordered list of the dimensions, the size of those matrices is invariant, so I'll use that. But there's a warning here, as Bart also mentioned, that there are way too many morphisms. You have to be very careful, and especially when you read the Eastern Europeans, they're not always clear which morphisms they take. Are they taking star algebra maps, are they taking unital maps, and so on and so forth. So you have to be very careful. And the standard book that I use on this by Gooderl, he himself says that, Gabriel Letters. Be very careful when you read the literature. Lots of mistakes. So Bradley in 1972 developed something called an AF seastar algebra. That's approximately finite seastar algebras. And these are very simple. They're just unions of those finite dimensional seastar algebras. So you take a countable family, countable colimit, or a countable directed set of AFC, of these matrix algebras. And you have to use star algebra. And these are what Bradley introduced, and the point was that he showed they have very standard forms. So let me show you what they look like. If you have a direct sum product of matrix algebras like that, and if you wanted to map into a particular matrix algebra size ni, what would you do? You just take a list of K matrices of sizes shown, and you just stick it on the block on the diagonal. Okay. Just stick it on a diagonal. How many times? Well, those are these multiplicities. How many times you stick it on? What does it have to do? It has to be a matrix. It has to be well defined. So you have this so-called combinatorial identity. That's the fit. And then a standard map then, what's called a standard star map, just takes such a list and just maps it to a list of these diagonal blocks. And that's called a standard map. So I'm sure Prakash probably knows all this. And AFC star algebras then are isomorphic. Bradley's theorem is isomorphic to colimit these such things with standard maps. The main thing that he was famous for is not just this theorem, but his graphical language that he introduced into this. These are called Bradley diagrams. They've become a big part of combinatorics by itself. So what you have is a list of vertices and edges, and you have a root, and then the associated to only adjacent levels of the vertices, you have these lists of those sizes of those matrices. And then how many edges, you put directed edges down, how many edges do you put from mj to ni, exactly that Sij in that matrix. Okay, fine. I'm going to come back to those. There's something called a K0 group, and I don't think I have time to say except to say that you start with some idempotents in an algebra, and what you want to do is get an abelian group out of it. So what you do is you look at equivalence classes of idempotents, and you want to add classes, and you want to get a cancelative monoid. And what is a cancelative monoid? It will be a commutative trace monoidal monoid. Let's just write equation here, x tends to u is y tends to u, x equals y. So you want to get that, and so in order to do that, how would you do it? How would you add these two things? Well, if you have orthogonal idempotents floating around, that's fine. If you're an effect algebra person, you just say, fine, it's undefined, never mind. But if you're a standard mathematician, you have to say, no, I need to be able to add idempotents. And so you move to a higher dimension by moving into a matrix algebra. You stick them on the diagonal with diagonal blocks, you form some matrices. In order to guarantee you have a cancelative monoid, you need slightly stronger idempotents than you usually have. But then you get a cancelative monoid, and you do the int construction that gives you an abelian. And that is exactly Grotius. Okay, and the same thing works for seastar algebras. There you have to use self-adjoint idempotents. They're called projections. All right. So, and then Medici had the following theorem that the category of AF algebras with lattice ordered K0 is isomorphic to countable MV-Algebras by an extension of his gamma function before K0. So, what are these algebra effects? So that was one thing. So now out of left field come the physicists. So Foulis and Bennett tried to give an abstraction of the algebraic structure of certain effects. And these effect operators that they noticed had the property that they were partial commutative monoids. So here I'm using clean equality, left-hand side defined if the right-hand side is defined. If only if the right-hand side defined are equal. So take partial commutative monoids, you demand they be orthocomplemented. This will mean, I'll take this to mean that the left-hand side is defined and is equal to that. And there are various millions of different axiomatization. Some are quite tricky to show are equivalent. For example, this one, you just take partial commutative semigroup. But anyway, that's what you have for effect algebras. And the canonical examples, you start with an ordered abelian group, an ordered unit, and just take what we were looking at before, the integral. And as a special case of that, for example, take the group of self-adjoint operators on Hilbert, bounded linear operators on Hilbert space, and take the integral between the zero and the identity. And the group here, the positive cone, are the positive definite operators. And then these elements in E of H, these effect elements here, are called unsharp measurements. And the ones which are projections are called sharp measurements. There's a whole theory of four kinds of probability theory, Gooder, where he talks about sharp and unsharp, quantum and classical probability. So then finally Bart has talked about predicates, and the proposition is if you have a nice category with sufficiently nice coproducts, then the predicates form an effect algebra. We'll talk about the various examples from, for example, take finite stochastic REL and various other examples. These all form sub-effect algebras of 0, 1, 2, x. There are lots of properties which I'll skip. I should say that MV-algebras look a lot like MV-effect algebras. You might think, gee, are they related? Well, there's a funny axiomatization which the Eastern Europeans have worked in great detail, and they show there's a bijective correspondence. I think it's actually a categorical equivalence between these notions. But I'm going to skip that because the most interesting, I think, equivalence is by Bennett and Foulis, who proved that an effect algebra is an MV algebra if and only if it's lattice ordered and has the Riesz decomposition property. Now, the Riesz decomposition property has many forms in the world of ordered unit groups, but there's only one form, basically, that works for effect algebras. They're all equivalent to unit groups. It's like Riesz interpolation, there's various things. But what it says is if A is less than or equal to a sum, then you can write A as a sum, where the sum ends have the property that A is a sum. And there's universal groups, which I don't have time to do, except to say that there's a kind of canonical way associated to any effect algebra of getting a kind of a universal k-dot measure. And that is, that's an development. Finally, inverse semigroups. I'm slowly getting to the subject here. What do I have?
Introductory part is over.
Right. So an inverse semigroup is a semigroup where every element has a pseudo-inverse that satisfies it. Unique pseudo-inverse. It's the same as saying that has an inverse and idempotence. And the fundamental example is partial bijections on the set. This is the fundamental example. And so I'm going to leave that, except to mention the idempotence is actually the partial bijections. And you can also do pseudogroups, which arise in differential geometry, and tiling semigroups, and various things. There's even a non-commutative stone duality, which is deeply based on this. So let me leave that for now, Prakash. I'll tell you offline about this. But I wanted to mention, let me just show you now some of the main results. So there are two fundamental congruence relations on inverse monoids. One is the J relation I've already mentioned. A is J related to B, means the principal ideals are the same. Another one is so-called D relation on the idempotence. E of S is the idempotence, which says E is D related to F. If you can think of A as a map in the grouping envelope between its domain and its codomain, which are idempotents. And it turns out that in all the inverse groups we look at, these two relations are the same. So if I take I'm going to be interested in those kind of inverse semigroups where the idempotents form Boolean algebra. These are called Boolean inverse semigroups. And the theorem is that if you take the quotient by this D relation, you get a well-defined partial commutative monoid satisfying Riesz decomposition. And if, moreover, D preserves complementation, you get an effect algebra. That's not too hard to prove. And the coordinatization theorem says the following, that if we consider such completely semi-simple is a technical word, which I won't mention, it was on the previous slide, a Boolean inverse monoids, and if D preserves complementation, I'm going to call them Foulis monoids. So Foulis monoids have the property that because D is equal to J, if we look at the quotient here, ES mod D, we can identify it with S mod J. And so if, in addition, S satisfies the lattice condition, then S mod J is a lattice, and then by the previous result I mentioned, Bennett Foulis, it's an MV algebra. And the theorem then is every countable MV algebra, there's a Foulis monoid, which satisfies the lattice condition. So that's the result. Now what do I have, 2 minutes?
1 minute.
1 minute, okay.
That's enough for the proof.
You can redo everything I did before for matrix algebras, looking at root matrices, 0, 1 matrices. Redo everything. And what you get then is what you associate the algebras in the representation theory, associate these MI, you put in direct products of these partial bijections. And you take colimits of those, and those are AF inverse modules. And those are used in the middle of the proof that you get these coordinates. What happens in the most interesting, okay, so let's talk about chains and make colimits of chains and inverse modules and so on. The point is these things arise from Bradley diagrams. That's the main thing. And then the example, which I won't have time to tell you about, is the Kuntz work, how to coordinatize the Kuntz, the dyadic rationals on the Cantor space. And these lead to prefix codes. And there's a certain amount of measure theory that's needed in the middle to make these models. So I think I'll have to stop there, but I'll again wish Prakash happy birthday.
Question from Prakash.
If it was your intention to throw me away and render me speechless, you did that very well.
It was meant to amuse you.
No, I'm highly amused. I look forward to spending about 3.5 years learning all this stuff. Just one question. So you mentioned a whole bunch of things, but amongst other things you mentioned car algebras and Fermi gaps.
Well, yeah, that's a terminology
Can you
that...
or not actually know what those mean?
Oh, okay. I was going to say that's the terminology of Medici, yeah.
But what, so do you know what car algebras are? They think that car stands for canonical anti-commutation
Yeah.
relation, right? So I was wondering if you could just tell me in like 10 seconds or less, what is the connection between those things and the algebras?
Just simply that algebra. You get the same.
Just an example?
Yeah.
But there was something across the table, right? Between car algebras, you had this list.
Oh, yeah. The car algebra is this. That's the coordinatizing dyadic rationals. So it's exactly the coordinatization model of the rationals, of the dyadic rationals in 0, 1. So it's the MV algebra of dyadic rationals.
Completely unexpected.
Yes, this is completely why.
Yes?
There's a little bit of teasing that maybe there was a connection with what I was saying yesterday. So I'm curious.
No, it just looks similar because you mentioned the projection. Those things, and it's just, maybe they had nothing to do with it.